Gary, do you see a shadow on that, on what's being displayed? Okay. All right. Don't forget that homework number 7 is due this Friday, and I'll never fear. I'll have another homework that I'll be handing out to you at that time. What I want to do first of all here is I want to go back a little bit and just do a couple of other examples on this thing where we're doing a double integral and we're reversing the order of integration. We went through a couple of problems where we basically had to reverse the order of integration because we couldn't find the antiderivative with the given order of integration. Okay. Now here we're not going to actually evaluate things, but let's suppose that this is the problem that you're given. Double integral, a y goes from 0 to 2, x goes from 0 to y squared, some function f x y dx dy. And you're instructed to reverse the order of integration and then probably then evaluate the integral. Now, to do this, you really have to draw a diagram here. All right, so here's our y and x, and it might help to just put a little note out here. Now, x goes from 0 to y squared. Y is going from 0 to 2. All right, so let's see. Let's go up to 1, 2 here. So y is going from 0 to 2. That's vertically. Now, horizontally, x is starting at 0 and then going to x equal to y squared. All right, going this way. So x equals y squared is going to roughly look like this. Okay, it's going to be a sideways parabola. All right, and then let's just draw that horizontal line over from 2 until it meets the sideways parabola, and let's figure out what point we have there. Well, here, x is equal to y squared right here. This is x equals y squared. So if y is 2, that's our y coordinate. Our x coordinate has to be 2 squared, or 4. So that's the point right there. And so in this case, we're integrating first with respect to x from 0 to y squared. So we're treating this that would be a type 2 region. And I don't really care whether you remember what the type 1 or a type 2, but understand that here we are first integrating horizontally with respect to x and then vertically with respect to y. Okay. Now, we want to basically reverse this so that we're first integrating with respect to y and then integrating with respect to x. All right. So if we're first integrating with respect to y, that means we're going to go from y equals something to y equals something. We're going to have a vertical arrow here now. All right? Okay. So what's our lower limit here for the y? Okay, this curved line here, this is x equals y squared. We want to put it in terms of y, so we take the square root of both sides. and it's y equals the positive square root of x, because it's up in the first quadrant. All right, so that's going to be our lower limit of integration here for y equals the square root of x. Our upper limit of integration, we can see here from the formula, is y equal to 2. And of course, we're going to have our function here that we're integrating. And then let's figure out our x limits. Now here, so we've gone up to do the y. We now have to cover our x's here. Well, what values of x are involved here with this diagram? Starting at 0, good. What's our upper limit for the x? 4. X equals 4. We have to integrate with respect to y this way, but then we have to cover all of our x's here, 0, and remember this point here has an x-coordinate of 4. All right, so this is what our integral would look like with the order reversed. You have to draw a diagram, otherwise you're going to, I know I'll mess it up. Now, you might be better than me visually. That's entirely possible, but I know I'll mess it up if I don't draw a diagram. Let me do one more. Let's see here. Let me kind of keep some of that on the board here. The second one, then, is we're given the integral from this time from x equals 0 to x equals 3, and then y equals minus 2x plus 6, y equaling 6, our function fxy, dy dx. So this time we integrate first with respect to y. First integrate with respect to y. So let's get a diagram going on this thing. Okay, so let's get our axes here. All right. Now, with this one, y goes from minus 2x plus 6 to 6. So first of all, let's draw 6 here. 1, 2, 3, 4, 5, 6. Here's 6 right here. And then let's map y equals minus 2x plus 6. Well, let's see. When x is equal to 0, y is equal to 6. So right here, that's a point on the line. And this is an easy way to graph things. And then when y is equal to 0, we have minus 2x plus 6 equals 0. So x has to equal 3. So let's go 1, 2, 3. So this line here, connecting these 2 points on the axes is this right here. All right. So this is the line y equals minus 2x plus 6. So we're going from, initially we're going here from this straight line here, and y is going up to 6. All right, so we're going vertically first. And then we go to x, and x is going from 0 to 3. Well, here's 0, here's 3 where it crosses. So therefore, let me put a line up here, and this is the area over which we are integrating that triangle. Okay? Now, what I want to do now is, I want to now go y equals something to y equals something, but I want to start with x equals something to x equals something of fxy dx dy. So now I want to switch the order of integration, so I want to first figure out what are my limits for x. So this time around, I'm going to be starting out with a horizontal line. We're going from the lowest value of x on this triangle here to the biggest value of x. So how can I represent the lowest value of x here? You have to do a little bit of work to do this. Notice that straight line, that represents my lower values of x as we go across, right? But the area that we're talking about is this area right here. So that straight line gives me my lower value. If we're looking for x values, we're getting bigger as we go to the right. But that line, as I've written it, is y equals minus 2x plus 6. What do I need to do with that equation? Okay, so y minus 6 divided by negative 2 equals x. I need to get it in x in terms of y. So get x in terms of y. So I get y minus 6 over negative 2 is equal to x, and I can maybe make that look a little bit nicer. How about x equals minus 1/2 y, and then plus a positive 3. Okay. So that's going to be my lower, because now I'm going horizontally first. So that's my lower limit. X equals minus 1/2 y plus 3. What's my upper limit for x going to be? No. 3. For x, not for y. What's my upper limit here for x? It's 3. This is the triangle here that I'm integrating over. So x equals 3. All right. Now let's figure out the y values that are going to apply here. What's my lower y value that I've got to have? 0. My lower y value is 0. You're jumping ahead, I think. So my upper y value is 6. Okay. All right. So this is how it would look with the order reversed. Remember that for these double integrals, the outside limits of integration are always going to be numbers. The outside limits of integration will always be numbers, not some kind of formula. Right? Okay. All right. Question about those two examples. Yes, Jordan?
Yeah, I'm confused. It's like we're reversing order integration that solves this thing horizontally. Wouldn't the y value be going from 6 to 0, like from the right move and check?
Oh, okay. In other words, you're saying go from 6 to 0. All right. No, we want to go in increasing order here. We don't want to go in decreasing order. Basically, what happens here, as y goes from, the outside limits of integration here are 0 to 6, all right? Or as you're putting it, 6 to 0. So as y takes on any value here from 0 to 6, what basically happens is that gets plugged in here, all right? So let's see, when y is 0, if on the lower limit, x is equal to 0 plus 3, so x is just going from 3 to 3. And that is the correct thing. When y is 0, x is only going from 3 to 3. It's just that little point right there. When then we go up, say when y is equal to 3, as we're going up, then, well, let's make it 4 so I get a nice number. When y is equal to 4, on our way from 0 to 6, then x is equal to minus 1/2 times 4, which is negative 2. 3 minus 2 is 1. okay? And so basically, x then is going from 1 to 3. And then when y is equal to 6, we have x is going from 0 to 3. Negative 3 plus 3 is 0. X is going from 0 to 3. We don't want to, I guess, if you reverse the order of integration, you're going to get the negative of the correct answer, right? You will. If you reverse the 0 and 6, I believe the answer you get would be the negative of the correct answer. So if you just want to remember this, Jordan, you want to put your limits of integration in ascending order, all right? And I don't think I fully satisfied you, but I do want to tell you that that's what you need to do. Right. Anything else done on these two? I just thought we needed some more help with that, because you're going to see that on the homework. Okay. What we're talking about here, we're on this section 15.4, and we're still talking about double integrals. Here we're talking about different areas in which polar coordinates are helpful. So this is 15.4 continued, and it's double integrals with involving polar coordinates. All right. And I want to just put, first of all, the general formula up here that we got from last time. The double integral over R, region R, of f of xy dA. Now this is where we're integrating over is what's called a polar rectangle, which means that R is going between two values, A and B, and theta is going between two angles, alpha and beta. Something that I didn't put up here last time, I want to also include here. We must have beta, the top angle, minus the bottom angle. That needs to be less than or equal to 2 pi and greater than or equal to 0. I didn't put that on there last time. Those are our two angles. And what we found out that this equals is the following, where we integrate from theta equals alpha to theta equals beta, and then the first integral actually is R equals A to R equals B. We put our function in terms of polar coordinates. So I'm going to, instead of saying f of xy, I'm going to put f of R cosine theta, R sine theta. And then the dA gets replaced with R dr d theta. Very important, this extra R there. Don't forget that. Okay, so we integrate with respect to R first, and then with respect to theta second. Okay. All right. We went through two examples. I want to go through a couple more here today, where the examples that we did last time are limits of integration here. In other words, the R values and the theta values were all given plain old numbers, okay? So what we're going to have this time is where we don't just have numbers as our limits of integration. So now we won't just have numbers as our limits of integration. What we're going to have is that inside limit of integration is going to have some kind of function involved with it. Remember, we must always have numbers with the outside limits of integration. Okay. All right. So here we're talking about integrating over a more complicated region. Integrating over a more complicated region where R, the distance to the origin of ranges between two functions of theta. We're going to call them h sub 1 and h sub 2 of theta. Okay. So let me show you this diagram of what we're talking about here. Okay. Here is that in gray there is the region we're going to integrate over. Now notice how curvy it is here. It's not just a nice arc that we had the last time. Down below here, our R value down here, our R varies as some function h1 of theta. Okay, so that's our lower R. I'll put that in quotes, our lower R. Then outwardly, we have R out here varying as another function of theta. We call it h sub 2, and this is our outer R or the bigger R, however you want to call it, right? So when we integrate here first we integrate with respect to R, our R values are going to go from h sub 1 of theta to h sub 2 of theta. Now remember, and we have R, dr, d theta. Our theta values still go from alpha to beta, whatever we determine those are. Now remember, when we do this inside integral, theta is being treated as a constant. Okay, all right. So the first example, well, there's one other fact I want to mention here before we do the next example. I'll call this a fact. If fxy is just equal to 1, in other words, it's a constant function, then what we have then is the integral from alpha to beta, integral from h1 of theta to h2 of theta, 1, that's our function fxy, and then don't forget r dr d theta. What this turns out equaling is just the area of this region between those two curvy lines for r. So this equals the area of the region D in the xy plane. So down back to here, if I put a 1 in here for our f, and then integrate, what I obtain is the area of this gray region, right? And that's what we're going to be doing in our next problem. And you'll also have a homework problem wanting you to calculate area. So when you're calculating area with this, you're going to be using this formula for the area. Maybe I should need to put a little asterisk by this, okay? All right, so let's look at this example here. Keep that up here. Example. Find the area So I'm going to underline that, area enclosed by one leaf, of r equals cosine of 2 theta. Now, if you may or may not remember that we covered polar coordinates in last semester, and we looked at some graphs of polar coordinates, and some of them look like little clover leaves and things like that. So let's get an idea here of what this graph looks like. Now, what we had done last semester was, say on a test, I had a table that you could fill in some values, and from the table then get a rough idea of what this thing looks like, okay? So here, this is the graph of r equals cosine of 2 theta. So our table, and I'm not going to take the time to do this full table at all today, but what we do here, if you're generating a table, is you start with various values of theta, then you obtain the corresponding values of r, and you plot the points, all right? Remember, theta is the angle from the positive x-axis, r is the distance from the origin, all right? Now here, as theta goes from 0 to pi over 4, we're going to get something like this in this direction. Because when theta is 0, r is equal to the cosine of, I'll put it in here, theta is 0, r is the cosine of 2 times 0, which is the cosine of 0, which equals 1, which is the point right out here. And then when theta is equal to pi over 4, r is the cosine of 2 times pi over 4, which is the cosine of pi over 2, which is 0, which is that point collapsing back to the origin. Now, so this is 0 to pi over 4. We can continue this process. This leaf here is going to be pi over 4 to pi over 2. And then we're going to have continue here, pi over 2 to 3/4 pi. Continue here, 3/4 pi to pi. Continue, 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 and continue like this. We end up getting at what looks like a clover leaf, all right? Now, what the problem is asking us is for the area enclosed by just one leaf. So this is good enough. All the leaves have the same area, so let's just do the one on the right. What we have to know is, first of all, what is the angle theta right here, and what is the angle theta right there that are going to be my limits. I need to get my limits of integration. All right. Now, that upper limit of integration is going to be pi over 4. All right, that's going to collapse. I have shown here it collapsed back to 0. All right, so let's just start to write this integral here. Remember, we do the thetas on the outside, so I'm saying that that's going to be my upper limit of integration. So that's the one on the top. Now on the bottom, my value of theta on the bottom is going to be what? Negative pi over 4. Right. Negative pi over 4. So I put negative pi over 4. One thing that suddenly, I'm strange. All of a sudden I'm walking or driving or something, and I think, oh, what if? Does anybody ever think like, or I think what if with a math problem? All right. So I thought, well, negative pi over 4, well, actually that's the same as 1 3/4 pi. if we're going the other direction, right? Right? Thank you. Right. Yes. Yes, you can do that. Very good. You can do that. 0 to pi over 4 multiplied by 2. That's perfectly fine. But my thought here was, okay, this is also, let's see, 1 3/4 pi is what, 7/4 pi? Why couldn't I put my lower limit of integration at 7/4 pi? And that's where I realized that the difference between these two angles has to be less than, what did I say? The difference is less than 2 pi. Is that right? It has to be between 0 and 2 pi. So where's that thing that I had just drawn? Right here at the beginning of class. The difference of the two angles here has to be between 0 and 2 pi. If I make that 7/4 pi, I'll have a negative 6/4. It'll be a negative difference. Cannot have that. Because it would also completely change the answer. So that's why it has to be negative pi over 4. All right, so that's our limit of integration for the thetas. Now we have to do our limit of integration for the r's. Well, here we're talking about r going from here to here. So what's my lower r going to be? 0, right at the origin. R equals 0. What is the formula for my upper r or my outer r? Yeah, cosine of 2 theta. That's what my graph is. That's going to be my upper or outer r. How I got that? Well, first of all, let's reread the problem that we're given. Find the area enclosed by 1 leaf of r equaling cosine of 2 theta. So we drew the graph of cosine of 2 theta. My lower value for r here, if I'm integrating r, my lower value here is 0. Okay, because we have to have a lower limit. But my upper limit is going to be where r hits the graph. And that's going to be a cosine of 2 theta, because that's what we're given. All right? Okay. All right, now since it's the area that we're asking for, area, my fxy is just going to be the number 1. And then we have r, dr, d theta. All right. So we've done, I think the hard part is we've just set it up. All right? We've got our, yes, Stuart?
Wait, how do you get, 0 from the bottom?
Well, where does r start for? We integrate our r, where does the r start at? It goes from here. Remember, r is that line coming out from the origin. Where does it start at? What value? 0. Yeah, 0, right there at the origin. That's where the r starts.
So then I get,
How do I get cosine? Yeah. Okay, because our given problem is r equals cosine of 2 theta. When this directed line of r stops at the graph, and the graph is cosine of 2 theta. Okay, so that's why that's the upper limit of integration for r.
I get that 1.
1. I got a 1 because the problem is asking for the area enclosed by this. So that was that previous fact that I put up here. Where is it? Oh, right here. Previous fact that if we're looking for the area of a region, we put a 1 in for our function. Okay? Are you all right then, Jordan? Okay. All right. So let's now evaluate this. Okay. So we have to integrate the r. 1 times r is r. So that's r squared over 2. And our limits are 0. Whoa, I'm sorry. Yikes. What am I doing here? Yeah, never mind. I was right. Senior moment. R squared over 2. And our limit, lower limit is r equals 0. Upper limit is r equals cosine of 2 theta. So we'll have to figure that out. That's our inside integral. And then on the outside, we're evaluating from minus pi over 4 to pi over 4 d theta. All right. Okay, so let's plug in our limits of integration here. Now our bottom limit is just 0, so that goes away. So what we end up here is the cosine squared of 2 theta divided by 2. And we're integrating minus pi over 4 to pi over 4 d theta. All right. Now we come across that formula that we ran across last class, and you're going to run across again. So, again, we've got to rewrite the cosine squared of 2, this time 2 theta. Now let's remember, the cosine squared of theta is 1/2 times 1 plus the cosine of 2 theta. Let me write the sine one down while I'm at it. The sine squared of theta is 1/2 1 times 1 minus the cosine of 2 theta. Now this time around, we are given the cosine squared of 2 theta. So in this formula here, we have to double the angle, so we're now going to have 2 times 2, 4 theta in our formula. So this is minus pi over 4 to pi over 4. Let's put the 2 out here as 1/2. And now let's write cosine squared of 2 theta. So that's going to be 1/2 times 1 plus cosine of 4 theta, d theta. All right? Okay, now we can figure out the antiderivatives here. This becomes 1/2 times 1/2 is 1/4 plus 1/4 cosine of 4 theta. That's what we're integrating. Okay, so therefore 1/4, this is with respect to theta, so I tack on a theta, 1/4 theta. Now let's find the antiderivative of 1/4 cosine of 4 theta. Again, without going through all the u substitutions. Anybody hazard to tell me what I'm going to have? Exactly. 1/16 sine of 4 theta. Doing that antiderivative, we have a 4 here. We're going to divide by that. That gives us the 1/16. And of course, the antiderivative of the cosine is the sine. Short and sweet, you do that. It's so much easier when you can do that rather than having to fool around with a formal u substitution. Okay, here's our antiderivative. Now we have to apply the limits. Minus pi over 4 to pi over 4. Okay. And basically what's going to drop out here in both cases is when I apply 4 times pi over 4 for the sine. That's the sine of pi. Sine of pi is 0. And the same thing down here, when I put in the minus pi over 4 into 4 pi there, that gives me sine of negative pi, which is also 0. So the only thing I'm going to have here is 1/4 times the pi over 4, and then subtracting minus 1/4 times negative pi over 4. So I have a double negative. So I end up with pi over 16 plus pi over 16, and which is 2/16, which is pi over 8. Now, Jenna, doing it your way, which is probably the the better way to do it, if you were integrating just from the 0 to pi over 4, you would have gotten what? Pi over 16 as your answer, all right? And then you would need to remember to multiply that by 2 to get your final answer, okay? All right. All right. Any question on this example here? We actually, this formula that we've got up here, this is actually the same formula. If you go back in the book to where we were doing these areas in the last semester, that 1/2 r squared, that's part of the formula. Okay. All right, let's just look at one more example here in this section. And okay. Okay, what do we have to see? Find the volume of a solid that lies under the paraboloid z equals x squared plus y squared, and above the xy plane, and inside the cylinder, oh yes, x squared plus y squared equals 2x. Now, the only way to get started on this thing is you've got to draw a rough drawing here of what in the world we're talking about, okay? Just from looking at the words on the page isn't going to be quite enough. Now, I'll do my drawing, and then I'll show you the nice drawing the book has, okay? Mine isn't going to look so nice. Let's start with this thing, the cylinder, x squared plus y squared equals 2x. Now, we know that cylinders look like this, right? They go up and down, you know, and they're circular and all that. That's what they look like. What you need to do there to figure out what this cylinder looks like is you need to complete the square. Let's subtract the 2x from both sides. So I have x squared minus 2x plus y squared equals to 0. And then what I want to do is complete the square for the x. Okay, so I divide the negative 2 by 2. That gives me negative 1. And then I square that, which gives me a plus 1. That's the number that I need to add on the left and on the right. Okay, so what I then have on the left is x minus 1 in parentheses squared plus, and I'm going to write this as y minus 0 in parentheses squared equals 1. Okay, this is going to be a cylinder. Well, what's going to be the x and y coordinates of that central axis of the cylinder? In other words, this cylinder has a central axis that it revolves around. 1, 0, right. 1, 0 is going to be the point on the plane through which that central axis will go. Okay, so let's see here. dxy. All right, so for starters, let's see, this is the x coordinate, this is the y coordinate. So right here, where x is equal to 1, that would be that point that I'm talking about. The cylinder, of course, is around, goes around, and then it goes up and down. Okay, so it's going to go up, and it's going to go down. All right? Notice that the one edge of the cylinder is right there on the z-axis. Right? This has a radius of 1. Okay, are we okay with the cylinder? Now, what we're told is this solid, first of all, it lies above the xy plane. So let's just forget about what I just drew underneath the xy plane, because it lies above the xy plane. And then what else do we have? It lies under the paraboloid z equals x squared plus y squared. So what that is, okay, let's just kind of think what this looks like. When x and y equals 0, well, z has to equal 0. So that's a point right there on it. And then as x and y get bigger, the z values just keep going up, right? So this thing looks, and it's going to curve up as a paraboloid. So this thing is going to curve upward like this. Okay? This is my upper part right here. So what we're talking about in this messy diagram is this area between the xy plane down below and underneath this paraboloid, yet it's all within that cylinder. All right. So here, let's have a nice computer-generated drawing. All right, here is my cylinder. I don't know if you can, this doesn't pick it up as nicely as what I'm looking at. This is on page 1025 if you want to check it out. But that's my cylinder right there. The bigger thing there, that's my paraboloid, all right? And notice that everything stops at the xy plane. So what we're talking about here is getting the volume of this whole region that is underneath that paraboloid, yet still within that cylinder, and up above the xy plane. Page 1025. All right. So, let's see here. Now, this thing, because everything is nice and circular, it cries out, use polar coordinates, all right? So we're going to use polar coordinates here. So first of all, so we need to fix, so if we're using polar coordinates, we need to figure out our limits, or integration limits, for theta and r, right? Now, this is going to be, what we're talking about, these integration limits for theta and r. We're talking about looking at the xy plane and trying to figure this out. Now, okay, what we're told here, it has to be inside the cylinder, x squared plus y squared equals 2x. And we've already found out that this cylinder on the xy plane is going to etch out this nice circle where at x equals 1, y equals 0. All right, let's get this in terms of polar coordinates. What would be the right side of that formula in terms of polar coordinates? What's x squared plus y squared equal to? R squared. R squared, right? Remember, x squared plus y squared Pythagorean theorem equals r squared. So I'm going to replace x squared plus y squared on the left with r squared. Now, what does x equal in terms of polar coordinates? Yeah. Did you say r cosine theta? Yeah. R cosine theta is x. So the right side I'm going to replace with 2. I'm going to bring down the 2. The x is going to be replaced by r times cosine theta. All right. Now the thing is, this is my cylinder. I want to get, first of all, let's figure out these upper limits here for r. Let's bring everything over. I want to solve this for r. So let's bring everything over to the other side, and I'm going to factor. So r squared minus 2r cosine of theta is equal to 0. And notice I can factor out an r between both of these two terms. So I get r times r minus 2 cosine of theta equal to 0. So the two values of r that I have to have here are the following. My first factor is r equals 0. I either have to have r equals 0 to satisfy this cylinder, or r equals 2 cosine of theta. Those are going to be my limits for r. Here is r equals 0. As I go out, I'm going to end at the end of that circle, at the edge of that circle there, and that point right here is r equals 2 cosine of theta. So that's my limits for r. Now, I've got to get limits for theta. Notice all of this is over on the right-hand side of the xy plane. What do we think here? This circle here is represented as r equals 2 cosine theta. What are two values of theta that cause that r to be 0? That was another problem completely. This is now r equals 2 cosine of theta. That one had cosine of 2 theta in it. Different problem. What value of theta would cause this to be 0 here? Two values. Pi over 2, because cosine of pi over 2 is 0. So therefore, an upper limit here is going to be pi over 2. That's where it's going to crash right into the origin again. And then down below here, my other value of theta that's also going to cause it to r to be 0 is going to be minus pi over 2. So those are my limits of theta, going from minus pi over 2 to pi over 2. Because what we are doing here is we're integrating over this region in the xy plane. Remember, everything is trapped within that region going up. So that is our region we're integrating over. All right. So let's get this started here. So therefore, let's set up the integral. Okay, we start with theta. Theta going from minus pi over 2 to positive pi over 2. Then our inside integral is going to be r. R, the lowest one is 0. The outer one is r equals 2 cosine of theta. And now we have to put our function in here. Now, this region here, let's go back to this. We're talking about the region that's under this paraboloid and above the xy plane. So looking at my messy diagram here, we're talking about this region right here. What we have to put in here in our integral is our top or upper z minus our lower z. And I mentioned that the last time. So we want to look at basically, and this is just very informal, upper z minus the lower z. And that'll give us our volume. Okay, our upper z here is this paraboloid, z equals x squared plus y squared. Our lower z, we're told this thing ends at the xy plane, that's z equal to 0. Now, we're doing all of this in polar coordinates. So how can I represent that upper z in terms of polar coordinates? R squared, right. Z is equal to x squared plus y squared. Well, that's what r squared is. So this is going to be r squared. My lower z is 0, so I'm not even going to write it. But now remember, times what? Very good. Times r d theta. Please don't forget that extra r there. All right. So this is it. This is the integral now that we have to figure out. This will give us that value. All right. And there will be a couple little tricky things here with this integral, I'm afraid. All right. First of all, r squared times r, let's just multiply that together. That gives us r to the third power. All right. And then now let's start with the inside integral here. R to the third with respect to r. So that's going to give me r to the fourth divided by 4. And that's what causes us to have some extra steps here because of the exponent. And that gets evaluated. Lower is 0. The upper one is 2 cosine of theta. That's my inside. I put my outside then, minus pi over 2 to pi over 2 d theta. All right. Now this one, okay, now the lower value for r is just 0, so we don't have to worry about that. Now I need to plug in for my upper value 2 cosine of theta. So what that's going to give me is 2 to the 4th times cosine to the 4th. Okay, so 2 to the 4th is 16 cosine to the 4th power of theta, and it's divided by 4, all right? So that, of course, gives me 16 over 4 cosine to the 4th theta. All right. Yeah, we're going to be using the trig identities, but first of all, what we have to do here, let's see, this is cosine to the 4th. And we want to use that cosine squared identity, all right? So how can I use the cosine squared identity with cosine to the 4th? Well, yes, what? Yeah, well, that's what I was looking for. Cosine to the 4th is cosine squared times cosine squared, right? Oh, okay. All right. All righty. So here, let's put this. So this is, let me just rewrite this. So I'm going to rewrite this as 4 times cosine squared of theta, and then I'm going to put that cosine squared in parentheses and raise that to the 2nd power. All right. Then what we're going to do then is we're going to replace that cosine squared with our formula. So that's going to be 4, let me put some big parentheses here. Cosine squared gets replaced by 1/2 times 1 plus cosine of 2 theta, close my parentheses, and then that thing has to be squared. All right. Now, one thing that I just, you always want, I'm not always good at that, but you want to be on the lookout for things that make the arithmetic a little bit easier. Notice we're going to square the 1/2 and we're going to square this. But when I square 1/2, I get 1/4, right? Well, 4 times 1/4 cancels out to 1. So we can kind of just cancel those out right off the bat. And so what I have left here then is 1 plus cosine of 2 theta squared. So the numbers get canceled out. Now with this thing, I'm going to have to first of all FOIL it out, all right, in order to work with it. So let's FOIL, and I get 1 plus 2 cosine of 2 theta plus cosine squared of 2 theta. So notice what we again have is we again have another cosine squared formula. This time it's similar to the one we had before where we had the cosine squared of 2 theta. So I can replace cosine squared of 2 theta with 1/2 times 1 plus cosine of how many thetas? 4 theta. And let me write the first two terms here. 1 plus 2 cosine of 2 theta. And then plus. So there's a fair amount of work here. We haven't even done the antiderivative yet. All we are doing is getting this thing ready so we can figure out what the antiderivative is. All right, I'm going to combine the only two like terms that there are, which is 1 plus 1/2. So we get this, 3/2 plus 2 cosine of 2 theta plus, and now this 1/2 also goes over there, plus 1/2 cosine of 4 theta. All right. Alrighty then, now we can figure out the antiderivative, and then we'll take a break. Okay, so this is with, here, let me put this, so this is with minus pi over 2 to pi over 2 d theta. That's what we're doing here. Okay, 3/2, that's just going to be 3/2 times theta. Cosine, 2 times the cosine of 2 theta is going to become what? Yeah, sine 2 theta, because the 2 divided by 2 will cancel each other out. 1/2 cosine of 4 theta is going to be what?
1/8 times 4 theta.
Very good. 1/8 sine of 4 theta. Bring that 4 down to a 1/8. Derivative of sine is cosine. And then our limits are minus pi over 2 to pi over 2. All right. All right. A lot of this stuff, again, cancels out because the signs turn out to all equal 0 when we plug things in. So all that's left here when we plug things in is the 3/2 times the top pi over 2 minus the bottom pi over 2, which is a -1. And we end up, when we figure all this out, we end up with an answer of 3/2 pi. So that's the volume. That's a little, fairly challenging problem, I think, with all the limits we have to do, with all the switching around, using that trig formula a couple of times. So this ends this section, then let's take a 5-minute break. Hmm. Hmm. Okay, whoever's listening, do you guys see a shadow on the screen for the the document reader that's being displayed? Harry or Jerry, either one, do you see a shadow there? This is a test. There's no such thing as a break, ever. Never a break. It's just a pretend break. I do on the computer, but not on the smart board. Interesting. Okay. I've had the tech people look at this before. It seems like it's worse today than it was, say, Monday. And for us, when we see it displayed on the wall, it looks fine. But what I'm seeing, just like you're saying on the computer, I'm seeing a shadow. What about Eureka? Do you guys just see? Do you guys able to look at that without seeing a shadow? Do you have a smart board or something that you look at? I used to work in healthcare. Patient unresponsive would be one thing I can say. There's no response here, but I'm sure that they're there. Right, John? Don't go there now. I know. I don't know. I'm hoping not. Right. Okay. Alrighty. I think we'll get started here. What this, so that was section 15.4, double integrals. What we're going to look at tomorrow is actually triple integrals, so things will get even better. All right. But for right now, this next section is a little application section. So I'm just focusing on one of the applications that's talked about in this section. So this is section 15.5. General title is Applications of Double Integrals. But what we're going to be focusing on here are the concepts of moments and center of mass. This may ring a faint bell from the previous semester. All right. So this time, what we're talking about, we're talking about double integrals. So say we're talking about, we have some kind of flat sheet, and the name for that is, that the book uses, is lamina. So I'll go on and use this word that the text uses. And that this is in the XY plane. All right. And this flat sheet, think of like a stainless steel flat sheet, something. It has variable density. So the density, and by the way, density means mass over unit area. So if something's more dense, like a, how about what is it, a black hole? That's pretty dense. It has a lot of mass per unit area, okay? Density at the point x comma y, at a point there on it, is given by a formula, rho of xy. So this isn't a p, it's actually the small lowercase Greek letter rho. Okay, so let me just show a little picture here of what we're talking about. Here is our gray area, that's our lamina there in the XY plane. And in what we're doing, because we're going to be integrating over this, it's all being divided up into little squares. And each square here has an area. Its area is delta A. And in the center there, we pick a point, say, in the center of each little triangle, and we evaluate, plug that into our density formula, and what we get here then is the mass of each rectangle. So if density is equal to mass over delta A over area, then we can just multiply by delta A and say that mass is equal to density times the area. Okay? All right. So we're going to be using that formula there to compute the mass of this sheet. Yes? Okay. What that means is we're dividing this j times, all right? We have maybe m times. This is 1, 2, 3, 4. I stands for one of those numbers. It's a subscript. The j is maybe going here from 1, 2, 3, 4 vertically. So each one of these squares has a pair of subscripts attached to it. Like this one here, say this one right here. This is 1, 2, 3, and then 1, 2. This would have the subscript 3 and 2 attached to it. 3 this way, 2 up this way. That's what the IJ stands for. The star probably for them means they're wanting to have a special indicator that it's right there in the center of the rectangle. All right.
Well, yes, you're not looking at mark. How come something
probably because I'm just getting sloppy and you look at my notes, or the book's notes. Well, I'd have to look at the particular thing, but if we're summing over summing two different things, we're going to have a bunch of rectangles, one going along one of the indexes of summation, the other one going along the other index of summation, and generally what you're going to have then is two subscripts attached to each individual term, because we're summing up along two dimensions, all right? Okay, now another thing here from, I want to keep that over there. Another thing that we had looked at last semester was this. This is from section 8.3 if you want to look back. We defined the moment, so I'll put that in quotes, the moment of a particle as the product of its mass and the distance. Let me cross out the and put its distance from an axis. So let me try to elaborate a little bit on that. What we had looked at briefly last semester is here's the XY plane. We look at a particle that's located on the XY plane. Let's say that its coordinates are X and Y, all right? And let's say this little particle has a mass, and the mass is equal to some number m. Now, we have two distances here. We have a distance of this particle from the to the x-axis, and we have a distance to the y-axis. So look at here. This is the distance to the y-axis. How can I denote that distance? What would be the length of that distance? If our x-coordinate here is x, our y-coordinate is y, pretend that those are numbers. What would be the length of that line that stops? The x. It would be the x value. Length x. Similarly, if we want to drop down a vertical line to the x-axis, this particle has this distance is a length y from the x-axis. So what we had defined was this: the moment about the y-axis is equal to m, the mass, times x, the distance, to the y-axis. Similarly, the moment about the x-axis also is the mass m times the distance to the x-axis. Now this time the distance is the length y. There's a shorthand for this, and for the moment about the y-axis, the shorthand is capital M sub y. For the moment about the x-axis, the shorthand is capital M sub x. Okay. All right. Now, what we're doing here then, let me put this thing back up. What we're doing here is we're taking, okay, we've got this sheet, this lamina, we're dividing it up into little rectangles or squares. And we're taking a point right there in the center, and we're summing up, say, with respect to the y-axis, all the moments of all the points that are in this lamina. So we have this point times this distance this point times this distance, we just sum up all of these, and the point has a mass, each of these points have a mass, times the length it is from, say, the y-axis. So that's what we're doing here. We're summing up all of these distances. So I can say this, my, this is with respect to the y-axis, is equal to a double summation, just like we had talked about. I equals 1 to k, j equals 1 to l. This is just represents here, I'm summing up all the indices, say, horizontally and then vertically, of that center. Okay, with the moment to the y-axis, I have to take the x-coordinate value, xij star, that's what they're calling that, and then we multiply that, that's the distance, to the y-axis, and we have to multiply it by the mass. Well, the mass can be represented as the area times the density. So the density at xij, yij star times the area. All right. I get a similar formula when I want to look at the moment with respect to the x-axis. I again get a double summation. This time, though, I do the distance to the x-axis. The distance to the x-axis are the y-coordinates, yij, in each of those rectangles. And again, it's times the mass. Well, the mass is the same thing. It's the density at each of these points times the area. All right. So what we have these double summations. As we take the limits where the rectangles get smaller and smaller, we obtain a double integral. Okay. So taking the limits, as k and l our indices go to infinity, we get this formula. Asterisk. Mx is equal to double integral over our d, that's our domain of our lamina, y, rho of xy dA, asterisk my, double integral over our region, x times rho xy dA. Right. This is the moment with respect to the x-axis. And this is the moment with respect to the y-axis. Okay. All right. Now, there's something called the center of mass here of this lamina. Let me show you this diagram. So our lamina it's something like this. It's, variable density. There's a point right there on that lamina that if we suspended it, theoretically, if we suspended on this little rod or something like that, it would completely balance out. That's called the center of mass. It has that center of mass. And the definition of the center of mass is this. Let me put this here. Center of mass This is the point, and they usually put a bar over the x and the y. This is the point x bar, y bar, such that m times x bar is equal to capital My, m times y bar is equal to capital Mx. This m here and here, this is the entire mass of the lamina. Okay. Something that I find a little confusing is just the fact that, okay, we have x bar in the formula on the left, we have x bar, but on the other side of the equal sign, we have capital My. All right? Now, the thing is, this capital My, this is the moment about the x-axis, all right? Because the distances are the y. So this is the moment about the x-axis, and so that's connected with the x bar here, moment about x-axis. And here we have the y bar on one side and capital Mx on the other, but this is the moment about the y-axis. All right. So if we divide both sides of this equation by the m, we get this. We get x bar is equal to 1 over m. Now I'm going to replace my formula for capital My with what I have written right here. So that's 1 over m times the double integral over d of x rho xy dA. And then we get y bar is equal to 1 over m double integral over d of y rho xy dA. When you put these together like this, then you see that you've got the x and the x and the y there. All right? Okay. Now the thing is, how do I calculate the mass of the lamina? All right? Well, the mass of the lamina, remember, mass is equal to density times area. Okay, we can determine that the mass of the lamina, m, the mass of lamina, which is the m, or the mass of the sheet, is the double integral of over our region D of the density rho of xy dA. Okay, that's going to be the mass of the sheet. So basically what this formula gives, we can calculate our center of gravity here, center of masses. In the denominator, we have the mass of the lamina, which is calculated with this double integral of the density. And then in the numerator, we have the moment. Maybe I think I need to put asterisk by those two formulas here for the center of mass and for the mass of the lamina. All right. What I want to do here, I think in this we have time to look at one example. I want to find, let's do this example. Find the mass and the center of mass of a triangular lamina and it gives us the vertices. With vertices 0, 0, 1, 0, and 0, 2. And we also need the formula for the density, where rho of xy is equal to 1 plus 3x plus y. All right. Now, we're going to get a double integral here. Let's make a sketch of this triangular region. Sketch the triangular region. Okay, we're given the three vertices. One is 0, 0. The other one is 1, 0. And the third one is 0, 2. 1, 2. 0, 2. So here's our three sides of the triangle right here. All right. This is our region, capital D. So we have this triangular sheet. All right. We're going to be doing a double integral over this. Now, I'm going to do the integral first with respect to y and then with respect to x. But you could do it the other way also. All right. This is both a type 1 and a type 2 region. So you could do it either way. I need an equation for that straight line. All right? All right. But I know 2 points that are on the line, right? I know that the line is on 0, 2 and 1, 0. So first of all, what's the slope of this line? Rise over run. What's the slope of that straight line? Negative 2. It goes down 2 and over 1. Slope is equal to negative 2. And what's the y-intercept of this particular straight line? 2. Y-intercept 2. So we can just do y equals mx plus b, like that. And so this line is y equals negative 2x plus 2. All right? Okay, so I want to integrate first with respect to y. So we're going to be going upward. So it's real helpful just to draw the arrow. And what we want to see is, where does the arrow start? Where does it end? So first, with respect to y, where does it start and what value of y? 0, yeah, y equals 0. And where does it end at what value of y? You've got to look at the formula there. The formula of that line, negative 2x plus 2. All right? Now, and then let's just put our outer integral then. That's our y integral. And over what values then are we integrating x? 0 to 1. 0 here, 1 here. And remember, Jordan, just put it in ascending sequence there, in numerical order. Okay, now let's see here. Let's first of all figure out the mass. We're asked 2 things, the mass. So the mass is basically this double integral times what we're integrating is, for the mass, is the density dA. So the density we are given as 1 plus 3x plus y. That's the density. And then we do it, let's see, we're doing this first with respect to y and then with respect to x. So this is what we have to calculate, the value of this double integral. All right. Now this gets a little hairy, and for time purposes, I'm not, let me just get it started, and then I'm going to skip a couple steps because it's just a bunch of, well, it's basically just that algebra stuff. All right. So here, let's do the inside integral first. We're integrating with respect to y, so we want to remember that x is a constant here, or treat it as a constant. So my first 1 becomes what? A y. What does 3x become? 3xy, and y becomes y squared over 2. All right, that's our antiderivative, and then we have to apply our limits. Here, y, the lower limit is y equals 0. The upper limit is y equals minus 2x plus 2. And you can tell already that since we have a y squared here, we have to plug in minus 2x plus 2, so we have to FOIL things out, so we've got to be careful with algebra. Let's put in our outer limit, 0 to 1 dx. All right. Now, the lower limit here is easy. When y is 0, that's 0, 0, and 0. So that's not bad. I am going to forego the algebra here on this and put down right here what this is. This is going to be 2x squared minus 4x plus 2 when the dust all settles. That's what we're going to get there. And now we're going to do the outside integral, 0 to 1, with respect to x. And this isn't bad. So we now 2x to the third over 3 minus 4x squared over 2 plus 2x. And we're integrating from 0 to 1. All right, so did I do, wait a minute, something, did I, wait a minute. Oh, I'm sorry. How about we just, I misread my notes. How about we just cancel out that whole bit right there? All right. And this is what we get when the dust settles with all of that stuff up there. We get this, minus 4x squared plus 4. So that thing really simplifies a lot. Sorry about that. Dx. All right. Now we do the antiderivative, minus 4x to the third over 3, and then 4, we tack on an x there, and then do our evaluation from 0 to 1. What we're going to obtain is a number 8 over 3. This is the mass of the lamina. Okay. I'm just going to do one of these because we only have 5 minutes to spare here. Let's figure out, so the next thing that they're asking you for is the center of mass, and that's that x bar, y bar. We've got 2 coordinates here. I'm just going to look at x bar right now. X bar is equal to, let's see, where was our formula here? It's equal to 1 over the mass times the double integral over d of x times the density dA. Okay, that's the formula. So this is going to be 1 over our mass. So for right now, I'm just going to put it like this. 1 over 8/3 times the double integral. Now, it's the same limits of integration that we had before. 0 to 1, 0 to minus 2x plus 2. Now, for this, we have to add in not just the density, but we have to multiply by the x. So we're going to have x times the density, which is 1 plus 3x plus y, and then we have dy dx. So this inside here, this is x times rho of xy on the inside. All right. Now, what we end up getting, now of course we're going to do the inside integral first, So again, we're going to treat x as constant. Let's see, let's just boil this thing out. This is x plus 3x squared plus xy. All right. And so we're going to treat x as constant. So we get as our antiderivative, our x becomes x times y. Our 3x squared becomes 3x squared times y. And our xy becomes x times y squared over 2. And we have to do some more fun algebra because now we have our lower limit, y is 0, upper limit, y is minus 2x plus 2. Out here for our outer integration, we have 0 to 1 dx. And then in the front of this thing, we're taking 1 over 8/3, so we're really multiplying it by 3/8, the reciprocal. All right. Now this whole thing, once I plug in my upper and lower limits for y, this is what I'm going to get. And now I'm going to put down the correct thing. Minus 4x third to the third plus 4x is what we get. And let's see, that's, well, actually, that's just, where's, oh. Yeah, right. And, yeah. And that's actually just the same as we had gotten before, except notice we're multiplying by x. So minus 4x to the third plus 4x, integral from 0 to 1 dx. And then in the front, we're multiplying by the 3/8. All right. So now we get the antiderivative of this, which is just like the one before. It's fairly easy to get. We have, okay, let's put the 3/8 down here. Minus 4x to the fourth over 4 plus 4x squared over 2, and we're evaluating it from 0 to 1. Okay. What we end up getting here is yeah, that's what we end up getting. We end up getting 1. So we have 3/8 times 1, and so our answer here is 3/8. Right. This is our x bar. That's the x coordinate of the center of mass. I do the same kind of thing to get the y bar, except with y bar, I have to, it's going to be 1 over the mass, which is 1 over that 8/3. But now I do the integral 0 to 1, 0 to minus 2x plus 2. This time for y bar, it's y times the density, y times 1 plus 3x plus y, dy dx. So it's y times this, and we go through the same process, okay? And for what we end up getting here is we end up coming up with a value of 11 over 16. So our center of mass then is x bar is 3/8 and y bar is 11 over 16. Okay. So this, where's my, oh, here's the triangle here. So basically it's kind of like x is kind of halfway, almost halfway over from 0 to 1, and y is not quite 1. So I don't know, it's somewhere like right there is our center of mass of that triangle. Okay, thanks for hanging in there, and I'll see you guys on Friday.